agenda for the day is we'll go through the hardware architecture of ASR. So these two devices.
I'm sorry, sir. Your voice broke for like 10 seconds.
Hello, is it better now?
Yes, sir.
Okay. So yeah, ASR 1K and ISR 4K are iOS XE devices, and ISR G2 it's a bit old, and most of these routers are towards end of life. And this runs the classic iOS software. We'll talk about what are the hardware architecture, how they are designed, and how it differs with the traditional differs from the traditional iOS routers. And we'll go through the software architecture as well. Finally, we'll take a look at how packets are processed in both iOS and iOS XE architectures. I'll also give a few examples of how the configurations get loaded from control plane to data plane. So that will be our agenda for the day. If you have any doubts in between, stop me and ask the question. That's fine. So let's start now.
Okay.
So SR1K devices, these are like these it's a family of the ASR1K family. It contains many devices like what we have depicted in that diagram below. So the ones on the left here, these we call them as fixed chassis, and these are modular. So what is the difference is the fixed chassis, the main components in these devices are the control plane, that is the route processor, and ESP, embedded system processor for the data plane. So those two modules will be fixed in these devices. You can't replace them. But here in these devices, it's modular, so you can replace the RP and ESP cards. So that is the difference here. And if you see the throughput as well, it increases from fixed to modular chassis. And the throughput here, it will be on the fixed chassis, it will be based on license. So as and when the customer installs license for higher throughput, they can enable higher throughputs. But on these fixed modular chassis, the throughput will be the line card rate that the FP, the forwarding processor, offers. So we can't have more throughput than that. So that is how we can calculate the throughput on these devices. So what features we have? So first one is as we see here, the line rate performance is from 2.5 to 200 gigs. It has dedicated hardware for traffic processing. So that hardware assists in ACL, QoS, and other features like IPsec and all those features. And it has a hardware-based QoS wherein it will be part of the QFP itself, the forwarding plane. And in traditional iOS, the QoS will be part of the CPU. So, but here we have QoS in the hardware itself, and we have in these devices. If you see here, we can host multiple RPs and multiple FPs. So that gives us redundancy. So if one of the RPs goes down, the state will be preserved by the other RP, and that takes over, causing no service outages. So that is one of the advantages of these devices. And we, in this kind of redundancy, we have something known as inter and intra chassis as well, where we'll have two different chassis, and we'll be having a redundancy between those two. So this is about the redundancy part, and we have instant on service delivery as well. Like there are certain chips that you can scale based on your requirements to enable enhancement in the throughput. So that will be, again, some of them will be part of some of them can be done through software licensing, and some of them can be done by upgrading the hardware. For example, crypto solutions in some of these ASR 1001X or 1002X, you'll have a default crypto chip, but if you want to increase the crypto throughput, then you can upgrade that particular chip, which will provide you more throughput. So this is a brief about how the chassis are, what they offer, the ASR1K family. Let's deep dive into how the internal hardware system works.
Samir, what does line rate mean? Like,
line rate in the sense it's the traffic that can be put on the wire. So the CPU might be, it is basically the throughput at which the chassis can, process the rate at which the chassis can process the traffic. So basically, this is a combination of all the internal traffic rates as well. So the limit will be set to somewhere around 200 Gbps. That is with the higher end FP modules, like there is something known as ASR ESP 200. So 200 stands for 200 gig. So with that, we'll get 200 Gbps of throughput. So line rate is basically the rate at which these forwarding planes, they process the traffic. So that is basically the throughput.
Okay, thanks.
Now, as I was telling, so these run iOS XE, and this right hand side has modular chassis, and these are fixed chassis. Let's take a look at the ASR1K building blocks. So as I was telling, the ASR1K, it segregates the control plane and data plane for better management. If you see here, the RP, which is the route processor, this one is the control plane. And in this diagram, you can see there are two RPs. One is active and one is standby. So that basically that is the redundancy. Each of the RP will have its own CPU. Interconnect will help the RP to connect with other modules like the other ESPs or SIP modules, MIP or ELC modules. And there is a GE switch which will give some of the built-in ports as well. Similarly, it will be there on the standby RP. The redundancy part that I was talking about earlier, what it means is if this RP which is active, if it goes down because of some software issue or something, it reboots, the state will be preserved here and it will continue working. The standby will become active, and once it boots up, it will be standby and this will continue to be active. So that is the redundancy part. So what RP is the control plane, as I was telling. So whatever configurations that you do, you will be doing them on RP.
Samir,
Yes.
so like
Yes.
at a time, only one of the RPs will be active?
Correct. Only one RP will be active at any time.
Okay. So is that not like a loss of CPU or something? Like we could have used both to have more traffic.
No, both can't be used because it's the decision that has to be taken, right? The control plane management, there will be conflicts. So only one RP will be used, and only on failure of that RP, the standby will take over. So that is the principle behind this, the redundancy part.
Okay.
And this is the control plane. The ESP here, embedded services processor. So this is the forwarding plane. So the forwarding plane, again, it has its own control processor. This is the CPU. QFP, this is the actual chip that takes care of all the processing of the traffic. And there is a crypto module as well, which helps in cryptography. Like it's basically used for IPsec traffic. So it helps in IPsec traffic. Again, we have two ESPs for redundancy. I mean, this is just an example. Customers can run only with one RP and one ESP as well. Having two of each is not a mandatory, but it will be better if they have, since it gives a redundancy. And there will be something for, the whole chassis won't go down if there is a breakdown of RP or ESP. There will be other module which will take over that will not cause downtimes. So that is the principle. and we have a mid plane in between. This mid plane is basically the internal link that connect all these modules together. The RPs, ESPs, and all these other SIP MIP modules, they communicate over this mid plane. We'll see what kind of links they communicate on. And a SPA is basically a shared port adapter wherein you will plug your cables actually. So these are again modules. These modules go into what is called as SIP, and SIP will have its own interconnect that connects to mid plane. And SIP, there is no, you can say there is no, these are kind of dumb modules. They don't have their own intelligence. Apart from just classifying the packets as high priority and low priority, they don't do much. The forwarding part is always taken care of the ESP. So these are basic building blocks. We'll see what each of them mean. So as I was telling, route processor is the one that handles control plane traffic and manages the system. Basically, here is where you configure your, you configure the new features or you delete them. The console basically will be on your RP. So this is the main entry to the chassis where you can manage the system. And the embedded service processor is the forwarding plane. It handles the forwarding of the traffic. Then we have SPA interface processors. SPA interface processor, or the SIP, what we call in short, is the was introduced as in the beginning. This was the first module, but then we we innovated with MIP and ELC. So these will have better throughputs. MIP, for example, gives us the option of having 100 Gbps. So these are different kind of line cards that we can use on the ASR 1K devices. Now this was with respect to hardware. For the control plane, let's see this thing. So as I was saying, mid plane is a circuit or the internal links through which these modules communicate with each other. So there is something known as integrated circuit bus, that is I2C bus. This will be used for system monitoring. So basically, the RP has to monitor the system, the entire chassis, whether they are responding or not, or whether the module is failing, whether the module is okay, it is performing as expected. So that will be taken care by the RP, and that will be done through the I2C bus. So if you see, there should be a link here as well, actually. So it will have a link to all of the modules in the chassis. And if a module is present, that will be monitoring the system. Like if you see there, temperature, if there is an online insertion removal, these platforms, they allow you to remove or add the modules when the chassis is powered on. So you don't have to power off the chassis to remove or insert the module. So that is online insertion and removal. So these things, they'll be handled by the this mid plane, the I2C bus. So this is basically for the system monitoring. Basically, the message is sent between these modules to check whether they are responding, whether they're active or not. So this will be taken care by the I2C bus here of the mid plane. And we have one more link, or the internal link, that we can call it's Ethernet out of band channel, EOBC in short. So this is a 1 Gbps internal link, which is used to push the configs, or push the configs in the sense program the system. These are hardware oriented, right? So they'll be programmed. Whenever you configure something on the RP, there'll be a EOBC switch in RP, which we have indicated here with GE switch. So what it does is, whenever you configure something, they'll be sent to the modules in the form of objects, and they'll be programmed into the hardware. So for that, we'll use EOBC link. And if you compare I2C and EOBC, the speed of EOBC is more because the system monitoring doesn't require much of the traffic to be sent, but EOBC needs more traffic. That's why I mean, higher throughput is needed in that internal link. So that's why we have around 1 Gbps for EOBC link. So this is how the system monitoring and system programming can be done from the control plane itself. And these are the internal links which we have in the mid plane that will help us in doing those activities. Going further, we have the forwarding plane architecture. So we have something known as embedded service interconnect. So these are the interconnects, as I was telling, they connect to the mid plane. So embedded service interconnect, or the ESI bus that we call, it's the interconnect that will connect all these SIP modules with, it's basically from ESP to all other modules. So if you see here, ESP can connect to RP or other three or any other modules like SIP, MIP or ELC. This will be called as ESI, embedded service interconnect, and it will have a throughput of around, it will have a speed of around 11.2 to 200 Gbps. So if you remember the first few slides where we mentioned that the throughput is around the maximum throughput that these devices support is around 200 Gbps. It is taken into account considering all these facts, like what is the throughput that is provided by the internal links, like these buses here in the mid plane. So 200 Gbps, it's the maximum limit that we have here. Okay, so so this was the ESI that we were talking about, the link bit, the interconnect bit from the ESP to all other modules. We have and for ESP, as I was telling, it's the forwarding plane. Except for the control plane, I mean the packets that are received from the management port. We'll talk about what management port is later. So except for the traffic which we received on management port, all other traffic has to move through the ESP. That's why we can call it as a heartbeat of the router. So if you see here, SPA, as I was telling, you will have some ports over there. You receive the traffic on the ports. It will be sent through the interconnect and the mid plane through to the ESP interconnect, through the ESI bus, and from ESI it will be processed here in the QFP, and the outgoing interface is determined, and it can be on the same SIP or any other module as well. Here we have shown it to be going through a MIP module, so it will be sent through the ESI bus again towards the MIP module, and a corresponding interface is chosen to put the packet on the wire. So this is how the forwarding works on a brief. So we'll deep dive into this later in the session. So this is basically the forwarding plane, how it works. Whatever the traffic enters the all these modules, it has to go through the active ESP. Any doubts till now?
No, sir.
Okay. So
No, sir.
yeah. Yes, yeah. Hello.
Yes, sir. No doubts, sir.
Okay, fine. So this is a chassis. How this is how a ASR 1006 chassis looks like. So as I was telling, these are the SPAs. So SPAs is where your line the ports are. So these white strips that you see here, each of these is a SPA, and this module that you see here that houses the SPA is called a SIP, the SPA integration processor, and this is the these two are SIPs basically. These two are SIPs, and these two are ESP, the forwarding planes, and these two are RP. So on the RP, you will have a management port which is the gig 0 here, and you will have a console cable as well, console port, and you'll have USB ports as well for the file transfers that you may want to do within the routers. So to copy the iOS image, I mean iOS XE image, or for during the upgrades and all those things, you can use this. So this is a view of the chassis. So yeah, this is a chassis view that we saw, and let's check the route processor architecture. So as we saw, route processor is for the control plane. It helps in managing the system. So this is the overall architecture of a route processor module. So this we have a multi-core CPU, which is the building block of this, and we have ESI interconnects here. So this is the ESI interconnect towards the ESP, the communication with ESP. I mean the communication in the sense the packets that have to be sent from ESP to RP, those will be sent through this ESI interconnect. As we were checking earlier, I2C chassis management bus is are those internal links that are used for system monitoring purposes. EOBC is the Ethernet out of band channel. So this will be used for to program the modules according to the configurations that are being added on the RP. We have a CPU memory which we call as DRAM. So this will be upgradable. I mean, it comes by default around 8 Gbps, and it varies on different modules. I mean, different devices, but the default will be around 4 or 8 Gbps depending on the model, 8 GB, and it can be upgraded to around 16 GB. So this is where the memory is allocated. I mean, memory for the processor will be present. So this memory will be allocated among multiple processes running on the RP, and that is where the this is also called as DRAM. And we have USB options, as I was showing in the image earlier. So this is basically to connect the USB for file transfers. In case of that, main usage for us is during the upgrades. If customers don't have any remote connectivity, that is when we use USBs to transfer those iOS or iOS XE images into the devices. So that is the USB here. Management Ethernet. So iOS XE devices provide a port called management port. The name will always be interface gigabit Ethernet 0. So that will be a management port. The main difference between management port and other ports is the management port is directly on the RP. So whatever traffic that comes from the management port will be directly to the CPU. It won't have to go through the ESP. That's why I was telling earlier, all the traffic except the management, I mean the traffic on the management port will be through the ESP. The management port will be directly to the CPU. And we have console and aux cable again to get the access to the direct access to the device. We have also an optional hard disk around, so that will also be there to store any other data. Usually on the higher end models like RP2 or RP3, we'll have this hard disk, and the trace logs and the core files that we'll be generating on the device, they'll be stored on the hard disk itself, and the internal boot disk will be of lesser size, and it won't be used for those things. We have NVRAM. NVRAM is the place where we store the configs. It will be persistent. It will be fetched every time a router is coming up, and those configs will be added into the running configuration. So running configurations will be in the CPU memory, and the startup configurations, which is the saved configuration, will be in NVRAM. Boot disk is the internal flash that will be used to store the iOS image and boot the system up. This is the default place where the iOS image will be stored, but we can also store the iOS images on a USB for temporary booting purposes. And we have Stratum 3 network clock circuit to exchange the to help to exchange the clock input and output with the other modules. So this is the route processor architecture. Any doubts here?
No, sir.
Okay.
No, sir.
Yeah. So as I was telling here, the memory will be required for the processes running on the RP. So this is where you'll get that memory, the DRAM. So it will be for processes running in RP plus the routing information base and forwarding information base at the control plane level. And it also determines the BGP table size. So basically, the BGP nowadays, if the ISP is providing us the full routing table, it will have around 8 to 9 lakh prefixes. So that would need around at least 4 GB. So with 4 GB, there are chances of memory running out. So the recommendation would be to use at least 8 GB of DRAM. So all those memory related things that will be used from here. And this one, the CPU, it will be running the operating system, and it will also manage the other modules. This one is, as I was telling, it is not a data plane interface. It is just the management. The throughput will be limited and the traffic will be directly to the CPU. So going on further with this is one of the latest RP3 is the latest route processor. So we have RP1, which is the oldest, RP2 intermediate, and RP3 the latest. So this is the chassis, how our RP3 module looks like. So these are the two USBs. This is the solid state drive, the hard disk, and this is the clocking. This is the management Ethernet that we saw. This is for the recommended to use only for the management traffic, and we'll also have a console and aux cable to access the device. This is the DRAM, the memory that we were talking about, the RP memory. So this is the DRAM, and as I was telling, the DRAM, it will be 8 GB by default and expandable up to 64 GB. We'll have a larger flash memory. 8 GB will be default for NVRAM content. We'll also have a dedicated crypto chip on this module itself, so which will help in processing the IPsec traffic. So these are
Sir, question.
yeah. Yes.
So what exactly is the management traffic?
Management traffic can be something like your SSH traffic. If you're SSHing to the device, right, to get the remote access or something, you can use the management port for that directly. I mean, if there is if you use the normal data plane, right, if the data plane is oversubscribed, if there is more traffic, there are chances of your management traffic getting dropped. So to avoid those scenarios, we have management port directly on the RP itself. So in those cases, there will be no, you'll have a direct access to the RP. So the management port takes care of it. The traffic doesn't have to go through a forwarding plane. So it will be direct RP. The management traffic can be, for example, SSH or Telnet.
Okay.
So this is a difference between RP2 and RP3. It uses a different CPU. RP2 uses Intel Xeon dual core, and this one uses Intel Broadwell quad core. If you see here, it's RP2 is again 2 cores, and this is 4 cores, and that's why it is faster than RP2. Default memory is same on both the sides, but how it is added, it's different. So if you see the arrangement of memory on RP2, it is 4 chips of 2 GB each, but on RP3 it is 2 chips of 4 GB each. Both at the end it will be 8 GB, but it is just how the arrangement is done. Memory upgrade option, at max on RP2 you can have 16 GB, 4 cards of 4 GB each, but on RP3 you have multiple other variations, 16 GB, 32 GB, and 64 GB. There'll be a built-in eUSB as well on both the devices, but the default size will be different. So this is the module where you can store your iOS images. For external storage, you will have HDD slot available. So this will be something that the customer has to buy in addition to the chassis. It will not be there in the route processor by default. And this will be an external USB option, and it will have other upgrade options as well. And the operating system on both will be iOS XE 64 bits, so that is the same. The chassis that they support, RP2 supports on ASR 1004, 1006, 1013, and 1006X and 1009X. The support of RP3 is limited to the latest chassis like 1006X, 9X, and 13. So that is the difference between RP2 and RP3. Going forward, let's take a look at the embedded services processor. So this is the forwarding plane, the module responsible for the forwarding of traffic. So we have it's a centralized forwarding engine with full packet processing abilities. So it provides us the BQS, that is basically buffering, queuing, and scheduling. So that is where the packets will be buffered before they can be scheduled and sent out of the devices. So it will have a different output traffic rates to carrier cards like SPAs, MIPS, carrier cards in the sense SPAs and EPAs. For other features such as traffic shaping, reassembly, replication. So basically for replication in the sense for multicast traffic, you get one particular packet and it has to be replicated to 3 to 4 different interfaces. So this is where the replication happens. Cryptography, as I was telling for IPsec traffic, the ESP has a crypto chip for that. Punt to RP in the sense, so since we have different modules here, the ESP will be data plane and the RP will be control plane. Any of the packets that are destined to the router. So for example, say if you are pinging ASR 1K device, so the destination IP will be on the device itself. So at that time, the packet has to be processed by the CPU. So it is at that point where the forwarding plane or the ESP module, it will send the packet to the route processor. That particular action where the ESP sends it to RP is known as punt. So that we call it as punt to RP. So ESP handles that as well. It can punt the packets to RP. It has a.
Sir, can you repeat that one once more?
Sure. So the architecture on these devices is segregated, right? Control and data plane. So say you are pinging a device, ASR1K device. Say we have a loopback or an interface IP, say 10.0.0.1. You ping that IP from a connected device. You receive that packet on the Ethernet card, the line card. That will be sent next to the forwarding plane, the forwarding processor, I mean. So forwarding processor determines that this packet is destined to the device itself. It shouldn't be forwarded again back to any other device. But the forwarding processor itself can't process that packet. I mean, the ping has to be returned again, right? It has to check, the control plane has to handle that. So in that case, the forwarding processor will send the packet to the control plane, that is the route processor. So that action there, where the forwarding plane sends the packet to control plane, that is called as punt to RP. RP is the route processor. We'll talk about the packet flow later. You'll get a better understanding.
Okay.
So as we were talking, we have the ESI links, the system buses that connect the forwarding plane to other modules. So they help in transporting traffic in and out of the QFP. Again, we have multiple names, but at the end the module is the same. QFP, ESP, FP, all these mean the forwarding plane. We have a CPU named FECP on these embedded system processor that manages the QFP and mid-plane links and all those things. It's a CPU for the processor, the ESP card itself. These are some of the innovations that were done from the earlier ESP modules. The ESP or the QFP, both are same. So we are now in the third generation of the ESP modules. The architecture can be scaled greater than 100 Gbps. The highest that we have currently is ESP 200 GB. So 200 Gbps is the maximum throughput. We have multiprocessor ability with around 64 multi-threaded cores, 4 threads per core. So these threads are known as PPEs on the QFP. We'll talk about them later in the upcoming slide. And it has the ability to prioritize the traffic based on the QoS and other features. So it has the ability to prioritize the traffic, making sure that high priority traffic is not dropped in case of oversubscription. As I was talking about earlier, it has the packet replication abilities for multicast traffic. If you just receive one packet and it has to be replicated and sent out of 4 different interfaces, the QFP handles that. It has the latency is very less. There is some feature called as packet trace, or the feature invocation array trace, FIA trace, what we call, where you can actually check what interval of time is being spent on a particular packet in the ESP, and it will be very less, in tens of microseconds, very less, and it is very less. I mean, it gives less latency and higher throughput. So this is about the QFP innovations from the earlier models. So this is a ESP20 block diagram, the basic architecture. Here the ESP20 means ESP is the embedded services processor, and 20 is the line card rate for that module. 20 refers to 20 Gbps of line card rate. Looking at these different components of the ESP, we have interconnects between the SIPs and the RP, which will help in receiving and sending the traffic across the multiple modules after the traffic is being processed. This is a crypto module that I was talking about earlier. So it will help in IPsec related, if it will help to encrypt and decrypt the traffic for the IPsec related packets. FECP is the main processor. So it helps in system monitoring, and it will communicate with RP for that. This will have its own processors running independently from the RP, and this is completely a processor for the control plane. DDRAM is the RAM memory chip for the forwarding plane. So here the processes that are running will be utilizing the memory from the RAM present over here. The boot flash, these will be boot flash and memory. It will be basically for storing the memory first before being actually programmed into the hardware here. So this is the QFP chip, the hardware chip that handles the processing. We have a few main components here. First one is global packet memory. So when the packets are received from the SIPs, right, the packets that are received from the other devices, they'll be put into global packet memory first here. So this will be around 128 MB of size. So this will be of 128 MB of size, and when the packets are here, it will then be put into a packet buffer, where it will be sprayed into these PPEs. It is in a random order. It's given to these PPEs. PPEs are the packet processor engines. So each of these will have its own threads that will be running, and each of those threads will be handling different packets. Once the packets are processed, they'll be put into this packet buffer here. It will be again 128 MB. So once the packets are put into packet buffer DRAM, they'll be ready to be sent out. So once they are stored here, the BQS, buffering, queuing, and scheduling, this takes these packets and determines the output interface, if the packet, where the packet has to be put into, or if it is destined to the device itself, it will be sent to RP, which is the punt. So this takes care of those, and it will also takes care of the QoS scheduling. All the QoS policies will be applied here, and if the packets are exceeding a particular bandwidth that is being configured, then the packets will be dropped. And whatever the drops that we see on these devices, you can see the QFP drops you can see at this level. And as I was telling, if a packet is hitting the device, there are very high chances that they'll be hitting QFP, and if they are getting dropped, we'll have to check on the QFP as well. So this is main place where it can get dropped. We have a TCAM where we can store, we can program things like ACL, QoS, and all those IPsec object IDs and all those things. So it will be limited in size, hardware based. So whenever a packet has to be processed by the PPEs here, it will take the information stored in TCAMs to apply different features and process the packet. This is the RAM memory which will be used by the quantum flow processor or the QFP. So this is basically a overview of the ESP. And as I was telling here, the system bandwidth is limited. So it depends on what ESP we are using. So it ranges from 5 to 200 Gbps. As we were telling, so BQS once it schedules the packets, it will put them into different queues. So we have around 16,000 queues on ASR 1001 and ESP5, and the number of queues will increase as the throughput or the line of the card increases. So we have multiple queues over there. So once the packets are processed, they'll be put into queues and they'll be sent out of the chips. And we have, as I was telling, the crypto module. This will take care of the encryption and decryption if needed for IPsec traffic. So this is that module. And the DRAM will have the memory that is needed by FECP, plus it will have QFP client driver. All these ACLs and QoS, before being programmed into hardware, they'll be stored in DRAM first, and then it will be stored into hardware and programmed into hardware. And this is where, as I was telling, this is a hardware level storage of the QoS, ACL, IPsec traffic selectors, and all those different feature values. So resource DRAM, it will be the memory that will be used by QFP. It will be used to store the dynamic values like QoS, mark, and policing. NAT sessions will be dynamic as and when a new NAT session is created. That will be stored in DRAM. NetFlow cache, the NetFlow, if you are aware, it will be grouping the traffic based on certain parameters like source based, destination based, or you can have L2 or L4 parameters as well. So that NetFlow data will also be stored here. And there will be per session data as well, like there will be firewall configuration as well, which we call as zone-based firewall. There will be NAT, NetFlow. All those data will be stored in resource DRAM. The next one is packet buffer. This thing. So as I was telling, once the packet is processed by the PPE, it will be put into packet buffer DRAM before being handled by the BQS. Any doubts about the ESP module?
No, sir.
Okay.
No, sir.
So this is the actual ESP processor, ESP module. So if you see here, this is the interconnect. From here, once you put this module into the chassis links will connect to this interconnect here, interconnect ASIC. And the chassis links will have the links to other modules where the communication happens between the ESP and the other modules. This is the crypto engine. This is the CPU of the ESP. This is the memory for the CPU. This is QF. This complete thing is a QFP subsystem, and which will have the PPs and the BQS. This will be the PPE DRAM, and this will be BQS packet DRAM. So this is the ESP module, how it looks like. So this is ASR 1000 ESP 100. So it offers around 100 Gbps of throughput. It again has the BQS functionality. It is a centralized, again, it's the same as ESP20, just that throughput is higher, and there are multiple enhancements, like it supports up to 23 Gbps ESI links to each slot, and FECP CPU is also upgraded. It will be around 16 GB memory, and it helps in managing crypto devices, mid-plane links, and QFP. So this is the ESP 100 block diagram. So if you see this diagram and the earlier one, let me just show you. Let me just bring that one here. So if you see this one, you have only one QFP system here, but in ESP 100 you have multiple two QFP subsystems. So that will help in providing more throughput. Rest everything is same, but each of the QFP will have its own resource DRAM and packet buffer DRAM, but the TCAM will be shared between both the QFP engines. And going with the ESP 200, we'll have 4 QFP engines. Each of them will have their there'll be 2 TCAM, and each of them will have their own resource DRAM and packet buffer DRAM. So this is like the enhancement in ESP 100 and 200. So if you see the number of interconnects as well, I mean the interconnect speeds that are offered will be higher in these modules compared to ESP20 or ESP40. That will ultimately enable higher throughput. So ESP bandwidth. So how to calculate the ESP bandwidth? So ESP bandwidth should be calculated based on the egress traffic, not the ingress traffic. It will be based on the egress traffic. So these are limited by the, as I was telling, it will be limited by the speed of buses that connect QFP complex to backplane ASIC. So it will ultimately depend on the buses like ESI, the throughput. The throughput will eventually depend on the internal bus links. So let's take a example, 4 different examples here. So let's say with ES100, now we have, this is the router, we receive 50 Gbps from one interface and receive 50 Gbps on the other interface. So if you see the total output traffic, it will be 50 Gbps here and 50 Gbps here. So total is 100, this is supported. So this is fine. Now, if we check the 100G, if we check a different scenario wherein we receive 10 GB multicast traffic with 8 times replication, that means we are sending out 80 GB of traffic, and in other flow it is just 20 GB of unicast traffic. So ultimately we'll be sending out 20 GB of traffic in the egress direction. So 20 plus 80, it will be 100 Gbps. So this is fine. If you check this one, we receive 50 Gbps in one side and 70 Gbps on other side. So total, both are unicast traffic, and the total bandwidth here will be 120 GB, which will exceed the capabilities of the ESP100 module. So only 100 Gbps will be forwarded. The remaining 20 GB will be dropped, and those can be seen as tail drops on the ESP module. So those packets will be dropped. Similarly, here we have 10 gig of ingress multicast traffic with 10 times replication. So that will give us 100 GB plus 20 GB unicast traffic. So only 100 GB will be transmitted. The rest 20 GB will be dropped because it exceeds the limitations. So these are ESP200. It has a different functionality.
Sir, actually, Saket isn't in this meeting. Actually, his laptop is hanging. So can you resume after that he messaged me?
So in ESP200, we have it uses 4 QFP NG-ASICs to achieve better performance. So what it does is each QFP NG is associated with a subset of SPA base and interfaces. So if you see this diagram over on the right side, so these 1, 2, and 3, these are handled by QFP0. These 3 are handled by QFP1. These 3 are handled by QFP2, and these 3 are handled. So whatever the traffic that is received, that has to be sent on these SPA base, they will be handled by different QFPs, and it's only for egress traffic, not for the ingress, and it should be taken into account for QoS and multicast. So whenever we see that there are some drops in some particular SPA base, we can, in ESP200, we can check at those particular QFPs. So let's take a look at how a data packet arriving on the SIP or one SIP gets processed by the QFP and is put into other SIP. So this is data packet that we see here. Now it is received on this SIP. It is sent over to the interconnect through the ESI link, and from the interconnect it will be sprayed into the PPEs, into the QFPs, in any of the 4 QFPs in a round robin manner, and so it will be sprayed into PPs on all the 4 QFPs in a round robin fashion. And upon when the packet is processed, there will be a forwarding decision made, and after that it will move to another QFP chip for egress processing. So it is processed for ingress packet. Now egress processing has to take place, so it shifted from QFP1 to QFP3. Here the egress processing will be done, and after that it will be again sent to interconnect, and through ESI links the egress interface, here in this case it is SIP5, so it will be sent to SIP5 and out of the corresponding SPA. So this is how packet flow happens on ESP module. Any questions here?
No, sir.
And similar to the ESP200, we have QFP-NG responsibilities here as well. So each of those are associated with a subset of SPAs. So this will be QFP1 and this will be QFP0. So QFP to interface mapping is very important. So the thing is, whenever the QFP, all the QFP, any QFP can take the packets from any interface and do the processing. As we were checking earlier, the egress will depend on certain, the egress queuing will happen based on the QFP to interface mapping. So as we were telling, if it is on for this slide, so if we say the egress port is on this SPA, it will be handled by QFP1 itself, the egress processing. If it is on any of these SPAs, then it will be handled by QFP0. So this is basically the QFP to interface mapping is. So slot numbering, when you see the chassis like this, it's very important to number the slots, because if there is some sort of scenario wherein you will have to remove any of the particular module and place it back. You will need to know which module exactly to remove from the physical view. So the numbering goes like this. For 1013, for example, we start with 3 SIPs at the bottom, SIP 0, SIP 1 and SIP 2. Then we have R0, F0, the RP and FP, the first the first modules. And then we have F1 and R1, and then again remaining 3 SIPs. And within each SIP, this is one SIP, this holder to this holder here. So within each SIP, we can house 4 spas, and the numbering is 0, 1 and 0, 1, 2, 3, like this horizontally. So this is important to know how the numbering is done for, as I was telling, during the scenarios where you'll have to replace or swap the modules, reseat, swap, or replace the modules. So coming to the SPA interface processor, so it's a physical termination of SPA basically. So SPA interface processor will house multiple SPAs. So this is a SIP module complete, and these white strip here, these individually they'll house one SPA each. So they don't have any intelligence of their own, and they don't participate in forwarding. They just send the packet towards the forwarding plane, and whatever the packets are received back, they'll put them on the wire. There are certain processes like IOCP which manages mid-plane links like ESI, IOBC, EOBC, and other SPA drivers as needed. There are certain, it has the ability to capture statistics of dropped packets. So we have something known as PLIM. So if there are any drops at the SIP level, we can check at the PLIM drops. So it has that ability to capture the drop statistics. And it does packet classification into high priority and low priority. This is basically in case of ingress oversubscription, it can classify the packets, and usually the low priority can be might be dropped, and it has a 120 MB buffer limit to buffer the packets in case of oversubscription. So if the QFP is not yet ready to take the packets from the SIP, SIP has the ability to store up to 128 MB of packet data. So this is the overview of a SIP module. Let's go to the SIP block diagram. So SIP again, it will have interconnects that connect to ESP. Again, ESP interconnect is known as ESI. So it will have the EOBC and I2C internal links that connect to RP for system monitoring and hardware programming functions. We have SPA ASIC, which is called Marmot, and it has an ingress scheduler which will help in buffering the packets and also classification of packets. This is IOCP is the control processor of the SIP module. It runs drivers and a Linux kernel. This ASIC it will queue the packets in and out both, and it has its own ingress and egress buffers, and these buffers will be per port. And these are the spas connect over here, and whenever the packets are received, that is ingress packets, they are classified. And egress packets, it holds the, so basically we'll have to, the logic here for ingress and egress buffers is ingress packets, the packets are buffered here if the ESP here is oversubscribed. And if the spas here are oversubscribed, the return packet that had to be sent out, they will be stored here in egress buffers. So that is the difference between ingress and egress buffers. Are you clear with that?
Yes, sir.
Okay. Okay. So SIP 40 to SIP ES. When we use SIP 40 with different ESP modules, there will be a variant connection. So say you have a ESP40 module, and which one is active and one is standby. So if you connect a SIP40, you will have 2 into 20 Gbps ESI links. But if you see on the ASR 1013 routers, there you can house five SIP modules. So no, sorry, 6 SIP modules. The first 4 will have the normal throughput, I mean normal links, that is 2 into 2 20 Gbps. But the last two, slot 4 and slot 5, will have 1 into 10 Gbps links. So though the throughput on those SIP modules will be limited. But with the ESP100 and 200, there is no such limitation. All the slots will have 2 into 20 Gbps ESI links. So this is only for the if the SIP40 is used with ESP40. So that is the only situation where we have this limitation. So this is the next couple of next few slides will show how the SIP interconnect happens between the ESP and the QFP complexes. So here in this case we have 10G interconnect and with a 10G ESI link. If you see 20 gig interconnect, you'll have 20 gig. For 40 gig, you can house more SIP. But if you see the last one, last two, you'll have only 2 links. I mean, a single link for this, 1 into 10 Gbps. 100 gig is again same. It will have a 140 gigs of capacity internally. So it's a quick overview of all the modular chassis. So the different chassis that we have in the modular section is 1004, 1006, 1006X, 1009X, and 1013. So you can see the number of RP slots available, ESP slots available, and different slots available. So RP slots available, 1004 has only 1, rest all have 2. ESP also same, 1, and rest all have 2. The SIP and MIP slots, it again varies. The ESR 1013 has highest 6 slots. Built-in Ethernet, there won't be any built-in Ethernet ports. You'll have to add the SIPs to get the Ethernet ports. Then redundancy, this is software and all these are hardware. This is software because we have only 1 RP slot. So we don't have the capability of adding 1 more RP for hardware redundancy. So this can be termed as software. So in the software itself, you can have 2 RPs running, but here you can have two hardware RPs. These will provide hardware redundancy, and these are different parameters like height, bandwidth, maximum output power, and airflow. This is the fixed chassis section. So we have 4 different chassis here: 1001X, 1002X, 1001HX, and 2HX. There are 2 others, but they are near end of life. They are 1001 and 1002. So these are comparatively newer products. And again, we have similar information here about these devices. These informations you can usually, you will get it in data sheets for corresponding chassis. So in many cases where you need to check what kind of EPS slots are there, what kind of 10 gig ports are there, you have to refer to the data sheets of the corresponding chassis to get those details. So this is just an overview. Let's see how a fixed chassis component looks like. So this is ASR 1002X router. So you can have 3 different spas here, 1, 2, and 3 slots, and you can have it's again a multi-core network processor will be there. Depends on that, 8, 16, 32, and 64. You'll have 4 packet processing engines. The PP is in the QFP, and you'll have 124 threads that are processed simultaneously. So that will give you higher throughput. And control plane as such, it will be quad core, and 4 GB default memory will be there. As I was telling, the throughput on these fixed chassis, it will be upgradable. So by default, it will be 5 Gbps. But if the customers need more and more throughput, they can enable that by purchasing the license, so that they can go up to 36 GB at max. And you can get a up to 4 GB crypto throughput. We have built-in input-output ports here. So 6 into 1 gig ports. So these are the ports, 6 1 gig ports, and all are SFP based. We can't use RJ45 ports here. And for management purposes, we have USBs, one RJ45 management port, and aux port, and a console port. So these are for the management functionalities. This is a 1002X chassis. This is a fixed, and the RP and FP modules will be built in and can't be replaced. So any hardware issues with those modules, the entire chassis should be replaced. ASR 1001X, it's kind of similar to 1002X. You have multi-core network processor and one SIP slot only. Compared to 1002X, which has three SIP slots. Control plane, it will have 8 GB memory and quad-core processor. Again, the throughput is based on pay-as-you-grow form. So 2.5 gigs will be default, and it can be upgraded. It provides up to 8 GB of crypto throughput. Similarly, we have management port, aux ports, console ports, and built-in we have the difference is we have 6 1 gig ports here. The ones marked in yellow, and the two marked in orange are the two 10 gig ports. So this will give us 8 ports in total. And we have the option for NIM SSD drive similar to ISR 4K. We'll have a look later how the ISR 4K has the hardware architecture. So this is 1001X. It's again the capability comparison between different modules. This is ISR 451X and 1001 and 1002X. So this is just for the details. Similarly, we have the ASR 1001 HX as well. The difference here is the crypto module is field replaceable. So as and when if you need more crypto power, you can just upgrade the crypto module. So that is the difference compared to X and HX modules. So as I was telling, HX models can be ordered with or without crypto hardware. Again, crypto can be upgraded if it was not ordered with the crypto module. Crypto bandwidth can be licensed from factory. Default will be 8 Gbps, but it can be upgraded on demand. But those crypto modules are not, they don't allow OIR, online insertion removal. The chassis has to be powered down to remove or install the module. This is a table of functionalities or the different parameters, the throughput, performance, clock rate that different ESP module provide. ESP10G, ESP20G, and these 4 models, they'll have their own ESP, and that will be the bandwidth will be depending on the license that we have on the device. And we have other 3 higher end, that is 40 gig, 100 gig, and 200 gig. So these are different ESPs available for the ASR 1K family. So any doubts till now? We'll move to ISR 4K hardware architecture.
No, sir.
Okay.
Yes, sir.
So ISR 4K devices, they are what we call as branch routers. So the ASR 1K, which provides higher throughput, is a WAN edge router, but these are branch routers which have comparatively lesser throughput. So ISR 4K, again we have cloud routers as well, which we handle CSR 1000V. It's a virtualized platform, so that can be hosted on the cloud. And we have others like ISRV. This is not that commonly used, but CSRV is commonly used. It's a cloud router, and we'll look at how ISR 4K, what is the hardware architecture, and what kind of throughput or other parameters that we can expect over there. So this is the evolution of the branch routers. So earlier we had Cisco 2500 and later it was 2600. Then came the ISR G1 family, 1800, 2800, 3800. Till these all devices are end of life, we don't support them anymore. From here, the few of the devices are nearing the end of life, these ISR G2 families. Then we had first ISR based on iOS XE, that was 4451X. Then we had 4400 and 4300 family, then came 4200. Then we have the latest ISR 1Ks, and most latest is ISR 4461. So these are different routers from the start with the branch, I mean, in the segment of branch routers. Let's see how the ISR, architecture is. Before that, this is the evolution of the throughput among from the different models. So this will give us 1.2 Gbps at max, and this is Gbps. This is 2 again, 2, 2, 4, 4, and 10. So the throughput increases, and it has a dedicated ASIC for control and data plane. And these devices, 4400 family, 4300 and 4200, these devices, they have single silicon with multiple CPU cores. So that is the difference. So these, since they have dedicated silicon, they provide a higher throughput facility. So ISR 4K, it functions based on default versus licensed throughput. So there will be a default throughput that is set for each of these platforms. The numbers that are mentioned in this slide are a default throughput, but with there are two types of licenses: performance license and boost license. Performance license, it increases the throughput. Usually it will be double what we have the default, but boost will be unthrottled. It will have as much as the hardware can process. So the throughput will be license based. If there is a need, the license can be purchased to enable more throughput. So this is the ISR family design, how it is. So this is a 4461 chassis. Similar to ASR devices, we have a management interface and USB port. We have front panel ports built in. So we have 2 gig ports and 2 10 gig ports. Sorry, we have 4 gig ports. These 4 gig ports and 2 10 gig ports. The specialty with the gig ports is these 2 gig ports are RJ45 based, and these 2 gig ports, it can be either RJ45 or SFP. These two sockets here that you see, this is the RJ45 and this is SFP. These two combined will be one interface. At a given point of time, only one can be used, meaning 000, this is 000. So 000 can be either RJ45 or SFP, not both. So there is an option. It can be used either as a RJ45 or SFP. But with 002 and 003, it's just RJ45. So that is how the built-in ports are. If there is a need for more ports, customers can add NIM modules or the service modules in these slots to get the higher number of slots. And service modules and NIM modules, they'll give other functionalities as well, which will be covered in later sessions. So 4461, the 44 is the ISR 4K, 4 is the family, second 4 stands for subfamily, 6 stands for number of NIMs and SM slots put together. Here we have 3 plus 3, that's why the number 6. So that's why the number is 4461. So we have CPU architecture where we have 4 core control. For control plane, we have 4 core processor, and for data plane, we have 16 core. That's why we will have a more throughput here. And we can have 3 NIM and 3 service modules. Front panel ports, as I was telling, we can have 2 combo ports. These two, as we were discussing earlier, these two are combo ports, and 2 RJ45 base and 2 10 gig SFP ports. We have power over Ethernet option as well, and it has the other specification about power and control services specification, the parameters here. So it again has the management port as we were discussing earlier. Similar to the 4451, but if you see the CPU architecture, the control plane is the same 4 core, but the data plane is 10 core, which was earlier it was 16 core in the 4461 model. So the throughput will be slightly lesser in 4451. And again, the third 5, it is because we have 3 NIMs and 2 SMs, total 5. So this is from the that number. Here there are 4 control plane cores and 6 data plane cores. We don't have any SM slots available, only 3 NIM slots, and that's why we have 3 over here, the number. And again, this has a PoE option and a management interface. Uh, 4331, it's again, you can have, this is a service module slot, and these two are NIM modules. So since we have 3, the third number is 3. It's a subfamily is 300, so 4, 3, 3, and 1. Here we don't have segregated cores for control and data plane. It's a 8-core processor, and it will handle both control and data plane. Again, 4321, it has 4-core processor, so slightly lesser throughput, and we don't have a PoE options in these, and we have only 2 NIM slots, no service module slots. 4221, again we have 4-core CPU and limited NIM support, no service module slot, and PoE option is also not available. So this is the software architecture of ISR devices. So the whole the processors will be divided into 2, control plane and data plane. So there will be a memory that will be shared between both control plane and data plane. So the memory will be 4 GB by default, but can be upgraded. The operating system for iOS XP, how it runs is, this is a complete package. So it will be Linux based. So the iOS operating system that we have, it will be running as a daemon process over a Linux kernel, and it can also host service containers that will enable the customers to use different services within the router itself. So when I said daemon process, it is nothing but it is a process that starts with the Linux kernel and ends with the Linux kernel. So it will be running in the background always. So that is why we have the name IOSD. It's a daemon process. And this is a data plane. Again, we have PPE is here, packet processor is, and BQS for buffering, queuing, and scheduling. They'll be sharing the same DRAM, but there will be fixed amount of memory that will be allocated for both control plane and data plane. So if you see here, fixed 2 GB for data plane only, packet buffering will have 750. QFP internal microcode, those PPEs will have 750, and XMEM will have 512 MB. DRAM has an increased size, and here you can extend the DRAM up to 32 GB. The PPE cores as well, you can see that they are more in number over here, and yeah, basically the DRAM is different, and there will be more cores. So data plane is 16 core here, but in the earlier one we had only 10 cores. This one. So this is 4331 architecture, 4300 platforms. So the DRAM will be shared between data plane and control plane. There will be no segregation of DRAMs. There will be single DRAM that will be shared between control plane and data plane. Similar in 4321 as well. 4321 and 4221, it will be shared. The difference here is the number of cores in data plane and control plane. On these devices, 4 data plane cores and 4 control plane. Here it is 2 cores in data plane and 2 cores in control plane. Any queries still here?
No, sir.
Okay. So this is hardware overview of the hardware design of ISR 4451. So this is the control plane. The main system management will be done, can be done from here. It will have 4 cores. You can run multiple service containers, and the IOSD will be running here as a daemon process. It will have its own DRAM, and we'll have PCI interface, 4 PCI interfaces, links between control plane and data plane. Data plane will have 10 cores and a BQS. It will have its own dedicated DRAM, and it will have front panel interfaces, the built-in interfaces. There will be a peripheral interconnect which will connect the ports, management Ethernet, flash, USB to the control plane, as well as the multi-gigabit fabric. These are the NIM or NIM and SM slots. You can have the NIM modules and SM slots. This is something that has to be discussed. So multi-gigabit fabric is a switch that is placed within the router. So basically what happens is, if you get the traffic that has to be switched within the same VLAN, the multi-gigabit fabric here, that itself will do it. It won't be sent across data plane. That will enable more throughput for the device. So only if the routing has to be done, then it will be sent to the data plane. If it is just the switching, the multi-gigabit fabric itself will handle. And if it is received from NIM and has to be sent across other NIM, it will be sent over here itself. But that multi-gigabit fabric, it won't come into picture for when we have the traffic on front panel, because front panel interface, the built-in interface, what we call, they are not directly connected with multi-gigabit fabric, so it has to come through the data plane and then switched across to the corresponding NIM card. So yeah, if you see that packet, if you receive from NIM and has to be sent out of front panel interface, it has to traverse through the data plane. So that will eventually affect the throughput, that the data plane throughput will be limited. So that throughput will be hindered. But if you see the packet that has to be switched within the same VLAN, the multi-gigabit fabric itself will take care of that. So the packet will never go to the data plane. It will be switched back from here itself. So that will increase the throughput that the data plane can provide. So the 4300 family and 4200 family, they don't have that multi-gigabit fabric. So all the traffic has to traverse through the data plane. So we have the CPU which has both the control plane and data plane processors. So it will have its DRAM and same USB ports. There will be a PCI switch that will connect to the NIM and service model slots. The GE switch that will be again connecting to the control plane. There will be a management Ethernet. I mean, this is a management port, and we have the I2C modules and console cables also for these platforms. So the course here, it will be enabled when the QFP license is activated. So by default, few of the course will be enabled, but if you enable uh, uh, the license, all the cores will be activated, which will better the throughput. So this is how the throughput can be increased. And the other two models here, 4331 and 4321, are similar, but just that there are less cores and less expansion slots like NIM and service model. Apart from that, the architecture is the same. As you can see here, 4321, the architecture is same, just that the service model slots are not there. We have just two NIM slots, and two cores will be for SFP, I mean QFP, and two cores will be for control plane. Oh, sorry, one core for control plane and one for crypto and QoS. So how we have something known as deterministic performance here. So as I told earlier, we can increase the throughput in these devices with the help of the license. So from the config from the CLI, if you increase the throughput level with this command, the throughput will increase, but it needs a reload. So this is how the throughput. This is the throughput that can be achieved with or without performance license. So this table, these two columns, you will get the number of cores enabled and maximum throughput by default. So these are default configuration, but with performance license, more cores will be enabled, and that will enable higher throughputs. For example, if you see 4451, 5 PPs will be there by default, which will give us 1 Gbps. But with performance license, 9 PPs will be enabled, that will give us 2 Gbps of throughput. So this is deterministic performance. So by default, you'll have certain throughput. If you want to scale your network, if you want more throughput, then you can enable it by licensing the same. So again, similar to the ASR1K packet flow mechanism, the incoming packets will be sent to either any of the PPs here. Once they are processed, they'll be put back into BQS, and the outgoing interfaces will be selected, and the packets will be sent across those particular ports. So the BQS is it's the same. The QFP is the same functionality as in ASR, but this is where the performance shaper lives. So we saw in the previous slide, we have a performance limitation on these platforms. So how do we limit that performance? So it is done in the QFP itself. So it works on a token bucket system. So basically, whenever a packet is being sent, or whenever the packet is being processed, few tokens are added, taken out of the bucket. So eventually, if there are no tokens, the packets will be buffered and it will be sent later. If there are new tokens in the bucket, the packet which is being buffered will be sent out. If there are less tokens, the packet will be sent, but with the negative recorded, it will be compensated later. So this traffic, the performance license shaper, it uses the token bucket system. Are you clear with this?
So these tokens, sorry, go on.
So okay, yeah. So once you get the packet, so leave this as a bucket full of tokens. So whenever you have to switch up, when you have to process a packet or forward a packet, you will take out tokens corresponding to the size of that packet. So say you have 100 tokens, you utilize all the 100 tokens. Now if no tokens are there, the next packet that comes will be buffered. So it will be put in the memory waiting for the tokens to arrive. The tokens will be freed when the previous packet is sent out. So once the packet is sent out, the tokens will be added back to the bucket. At that time, when we see that there are new tokens, the packet can be sent. But if those tokens are less than required for that particular packet size, we'll eventually send the packet, but with a negative record. so that the number of tokens will be negative, and when the new tokens gets added, it has to come above 0 for the next packet to be sent out.
Okay, sir. Yeah, one question, like, what is this? Like, how do we determine the number of tokens? Like,
that will be an internal mechanism. It is an internal mechanism,
okay,
but this is how it works. It's similar to the QoS mechanism as well, token bucket. So, but the difference is if there are less tokens than the packet size, in the normal QoS we won't send the packet, but here we'll send the packet with a negative record.
okay,
So again, this performance license is based on the egress packets. So what packets it sees is packets coming in from PPEs, packets addressed for external interfaces, and there will be no difference between LAN or WAN interfaces. All interfaces are the same, and it will be the performance license will be checked for all the interfaces. Now, how to check if the performance is being shaped? I mean, performance is being shaped in the sense if the traffic that is being processed by the device is going above the throughput level configured on the device. This is the command. If you execute this command, you will get to know the throughput monitor threshold. So there is if you enable this, there will be a log sent on the device whenever the throughput of the device is over the 90% of the limit, and it will only give the logs if the sampling period, if the throughput of the device is more than 90% for the last 300 seconds. If it's more than 300 seconds, then it will log a message like this saying average throughput rate approached the licensed bandwidth. So here we have 1 Gbps of bandwidth, and no, here we have 100 Mbps of bandwidth, and we had traffic of more than 90 Mbps for the last 300 seconds. So it will log a message saying we have approached the bandwidth limit. So if possible, the traffic can be reduced. If not, the throughput can be increased with a license. So we can use this log to say when we are actually crossing the throughput limitation. But with the command as well, we can check this. So here, this is both input and output. We'll have to check the output bits per second. Here, if you see, it's 99 Mbps, almost around 100. It will give us last 5 seconds, 1 minute, 5 minute, and 60-minute average. So since we are over 90 Mbps for last 60 minutes, we are sure that the traffic is more than 90 Mbps consistently. So we can either look at reducing the traffic, or we can look at increasing the throughput with the license. So we have 100 Mbps throughput limitation. What if we receive more than that? So in that case, similar to the ASR devices, we'll drop the packets with the reason tail drop, and we can check how many packets are being dropped with this command. So it will give us the packets that are being dropped because the throughput limitation has been reached. So this will give us the idea of what is the throughput that the device is currently providing, and if the throughput limitation is exceeded, what is the number of drops that we are seeing. So these two are the commands, very important ones. So we have something a license bandwidth oversubscription command as well, where we can see how many tail drops are being seen per interface because of the license oversubscription. In this example, we are seeing drops on gig 001, tail drops. This will be the bytes, and this will be number of packets. So basically, this will be interface with which is pretty busy. More number of packets are being traversed. So many drops are seen on this interface. So unthrottling the performance, there is something known as boost license, which is supported from iOS release 16.7.1 onwards. So if you, similar to configuring the throughput level, we have an option here, boost. So it will be unthrottled as much as the system can handle. So once installed, the performance will be very high. One more thing is the throughput, the boost performance that we say here, the unthrottled performance, it's only for the Ceph throughput. If there are any features that need the processor intervention, like the IPsec or crypto traffic, in those cases the throughput will be lesser. For the Ceph complete Ceph traffic, we can expect unthrottled performance. There are a few limitations, like on ISR 4300 family with the boost license enabled, container services can't be run. Majorly because the CPU cores will be involved in traffic processing, so it's not advisable. It's not supported to run the containers. So boost will only add throughput in cases where platform has reached the performance license limit. So if we are reaching the default limit, there is no need to install boost directly. We have intermediate step which is performance license. If we are exceeding the performance license limit as well, then the last step is to boost the throughput to the unthrottling the performance. So this is the boost performance working. So performance license will give us this throughput in different platforms expected at the CPU percentage. Boost will be 4 Gbps at 35%, but there will be certain limitations as well. Like as I said, it will be Ceph traffic only. Non-Ceph traffic will reduce the performance, and IPsec traffic, if it is more, that will also reduce the performance. So what is a service container? I was telling a service container can be run on these devices. So they use virtualization technology. So basically they run as a container on the Cisco iOS, on the Linux kernel of the iOS XE device, of the iOS XE software. They can be developed and released independent of platform release cycles. For example, a Cisco application, we have ISR WAS, and we have other like Snort or UTD. So these are different examples of containers that can be run. So basically, this will be there is a Linux virtualization feature called LXC. This one, LXC and KVM, kernel virtualization. So the both of them are leveraged to enable the service containers on these platforms. So that will help to have multiple different applications running on the routers itself. So this is how it works. We have Linux operating system that is running here. On top of that, we'll have one part as the IOSD, which is running as a daemon process, and it is a control plane. Here we'll be running the LXC and KVM. So KVM will be for the containers, for example, ISR WAS and the third-party applications. And we have this platform-specific data plane where we can have app now, which communicates again with the ISR WAS here, and it can apply its the feature can be applied on the packet. So that can be enabled with the service containers. Any queries till now?
No, sir.
Okay. So let's move on to ISR G2. So these are, as I was telling, these are older devices compared to ISR 4K and ISR 1K. These are almost near to end of life, after which we won't be supporting them. So ISR G2, they are not as much modular as ASR 1K devices, and they run iOS operating system, not the iOS XE. So this is a typical 3900 device. So we have gig ports, built-in gig ports, the console and aux cables. We don't have management interface here. We'll use usually the gig 00 will be used for management purposes. We have EHV slots to increase the performance, to add the ports and all those things. Service modules are also supported, which will help to bring in different technologies into the device, like a switch module can be added. There are internal service modules as well. Apart from that, we have the multi-core processor, and the multi-gigabit fabric is also present, similar to the ISR 4K devices. So this is the ISR G2 family. We have 1921, 1941 in 1900 family, and in 2900 we have 2901, 2911, 2921, and 2951. And these four are 3900, 3925, 3945, and 25E and 45E. So these provide higher throughputs, these routers, and as I was telling, most of these routers are towards end of life, and we won't be supporting them for longer time. The hardware architecture of these devices is very simple. We have a multi-gigabit fabric that connects to all the modules that can be that can be inserted. For example, internal service module, HVIC cards, and PVDM cards. So this will have a 1.25 Gbps internal link to the CPU, which can have, there will be 3 ports. That are added into the device. They'll be connected to the multi-gigabit fabric, similar to the ISR 4K model. So this is hardware connection point of view. So here we have how it works. So we have these modules where there is a controller. So the controller will take care of buffering the packets and sending an interrupt to the device. And there will be a system bus that will be connecting CPU to all those different modules, and the CPU will have the bus interface similar to the interconnect of ASR 1K devices. It will have its own flash to store the iOS images, NVRAM for the running configurations, the startup configurations, and we have multi-core CPU and a RAM for the processes running on the CPU. So this is a basic hardware architecture of the ISR G2 platforms. So regarding the iOS software, so this is the classic software that was started dating back to Cisco's earliest days, like since 1984. It's a monolithic OS in the sense it runs all the data plane and control plane modules in the same memory space. Like the ISR 4K, it doesn't have different data plane and control plane memory space. It will run on the same. So the disadvantage is if any of the process starts using up all the memory, then eventually the device will crash. But in case of segregated control plane and data plane, if any process on control plane is utilizing more space, then only the control plane will be affected. If the control plane reboots, if there is redundancy, the second control plane will take over, the second RP. But in these iOS devices, that is not possible. And also these devices, they don't provide the option of in-service iOS upgrades. So we have to reboot the device always to complete an iOS upgrade. We don't have a dedicated ASIC for packet processing. All the packets have to be software processed. So because of that, the throughput will be lesser. And the processes for each of those for multiple features will be running simultaneously, and they'll be sharing the same memory. And the memory will for the data plane will be what we call as buffers. So buffers will be something like small buffers, big buffers, medium, large, huge, something like that. So different kind of buffers will be there where the packets are put into and then later processed. So any doubts about this iOS architecture or software architecture?
No, sir.
Okay. Let's see how the packet processing. Let's see how packet processing is done on these iOS platforms. So when a packet is received on the interface, it will put the packet on the RX ring here and send an interrupt to the processor saying that a new packet has arrived. If the RX ring is full and it doesn't have any space, then the interface will drop the packet and it will increment those errors like overruns. And if there are any input errors like CRC errors and all, those will be incremented and the packet will be dropped. Now, say we once put the packet on the RX queue, then it will be put into the input queue or the system buffer pools, from where the processor will process those packets. So again, for processing, we have three options. One is fib table in case the CEF is enabled, route cache if cache routing is enabled, and IP input if we don't have these fast switching enabled. So the processor will process the packet based on these three, either fib table, route cache, or IP input. Based on the result, it will place the packet on the output queue. It can also place the packet directly on the TX ring itself. If the if the TX ring is free, then it will place the packet directly on the TX ring. If it is full, it will place the packet in the output queue, and then once the TX ring is free, the packets will be transferred from the output queue to the TX ring, and eventually the TX ring will put the packet on the wire through the interface. During this time, TX interrupt will be generated when the packet is being released and sent out of the interface. So if you see here, for one packet to be processed, we need two interrupts. One is RX interrupt, this one, and one is TX interrupt. So all these are CPU, all these are handled by the CPU. So that's why the throughput on these platforms is lesser, since the CPU has to get involved every time a packet has to be processed. This is the how the packet processing happens on the iOS platforms. Any queries about this flow?
No, sir.
Okay.
Sir, what are these public normal?
Those are particle pools, not applicable to all the iOS devices. Few of the older iOS devices had these particle, but basically this is the once the put in RX, it will then be put into input queue or the system buffer pools. Then the processor will process this packet. Okay, let's move on to iOS XE software architecture. How the architecture runs over there. So as I was telling, the iOS X combination of iOS process running as a daemon plus a few middleware plus the platform software, which is the Linux in this case. So this is how it runs. So iOS will be running as a daemon process. We'll have some middleware like chassis manager or forwarding manager, and then the platform software, which is the Linux kernel in this case. And this iOS process, as I was telling earlier, it will be running as a daemon process, which means it will be starting with the Linux kernel and ending with the Linux kernel. It will always be running in the background. And the command syntax and all those things, the look and the feel is the same as the iOS. So it is consistent in that sort. So we have different processes running on different software processes running on all of the modules. So on RP, we'll have different process running. On QFP, we'll have different processes running. On SPA as well. Chassis manager will be running on all the modules. Forwarding manager will be running only on the RP and FPs, not on the SIP modules, because as we discussed earlier, SIP don't have any intelligence on their own and they won't affect any forwarding decisions. So the forwarding manager won't be required here, but forwarding manager will be running on RP and FP, and all these processes, the chassis manager, forwarding manager, they on one module. For example, chassis manager on RP communicates with QFP chassis manager or the SIP chassis manager through the control messaging, through the internal links like the I2C and the EOBC that we were checking earlier. So this is how the software processes run on different modules of the iOS XE devices. Let's look at a few acronyms. So PMAN is the process manager, iOSD, the process iOS daemon, which will be running as long as the kernel is running. CMAN is chassis manager, IMAN is interface manager. So these are different acronyms that you'll come across while handling different cases or going through the architectures. We'll see how the architecture is and what different processes do. So reference hierarchy. So to understand how iOS XE architecture works, we have to understand how the reference hardware architecture works. So the reference hardware architecture gives importance to distributed hardware architecture. So basically, the hardwares will be distributed based on their functions. So RP will be control plane, FP will be forwarding plane, and we have other SIP modules where the interfaces are connected for IO complexes. So the softwares will be independent on all these modules and distributed basically, and they'll be coordinating with each other over these EOBC links. And the punt, as I was telling, if the packet is being sent from FP to RP, it is called as punt. So this is reference hardware architecture, which keeps the distributed hardware architecture in mind. So the hardware will be distributed, the functions will be distributed across multiple hardware modules, and each of those hardware modules will communicate each other to make the process work. So this is ASR software architecture. So as we were checking, we were seeing earlier, RP will have its own CPU, ESP will have its own CPUs, FECP and QFP. SIP will have its own processor, IOCP. On the RP CPU, we'll have the chassis manager running, which is running on other CPUs as well. The forwarding manager will be running only on RP and ESP, and the communication between these processes will be happening over EOBC and I2C channels. So let's see what a chassis manager is. As we were seeing earlier, the chassis manager will be running on all the modules, RP, ESP, and all the SIP modules. So what it handles is, once the RP boots up, it makes sure that all the other modules are also booted up. So it initializes the booting sequence of other modules. That is the function of chassis manager. It also manages hardware components, manages ESI links. So those are the chassis manager of the forwarding plane that will be managing the ESI links. So, and whenever a new device is being added or removed, the chassis manager is the process that detects that a new device has been added and makes sure that it is initialized and it boots up. So chassis manager, it also monitors the environment variables like temperature, fan speed, the voltage of the power sources, those parameters. So, and it will also always provide the alarms in case anything is beyond the threshold value. Also, the chassis manager, it selects the active standby RP and ESP, and it also makes sure that in case of failover, the standby takes over and the services are not interrupted. So all these functions are handled by chassis manager. Any doubts here?
No, sir.
Okay.
No, sir.
Okay. So similarly, we have forwarding manager, which is there only on RP and ESP. So it is again distributed function. It has different functions on RP and ESP. So forwarding manager, what it does is, whenever we configure anything on the RP, like ACL, SNAT, or the routes that are being learned from other devices, they'll be added into the routing table in the RP first, and then they'll be sent across to the forwarding manager on the ESP, where it programs it in the hardware level, and it sends an acknowledgement back to the RP saying the programming has been successful. So Fman RP, Fman RP and Fman FP, they communicate with each other to make sure that forwarding works as expected. PPP microcode. So as we have come across multiple times, PPE is the packet processor engine which have multiple threads which enable the packet processing. So these processes they process the packet and they run to completion. Run to completion in the sense, once they start, they run till the packet is processed and they end there. And when the next packet comes, they will be started again. So that is what run to completion means. So they help in they are registered by different memories which is present in the ESP DRAM, and they also help in FIA here is feature invocation array. So what it means is per interface, depending on your interface configuration, there will be two feature invocation array. One is input array and other is output feature invocation array. So they will have all the features that have to be applied on the packets when a packet is received or is being sent. So those feature invocation array components will be handled by PPE. So that is what we mean when we say the packet is being processed. It goes through all the features that have to be applied on the packet and applies the corresponding features, and then it will be sent to BQS where the packet is ready to be sent out. So those processing of the packet, it will be based on feature invocation array, which is a list of features that has to be applied to the packet per interface. So you can check it with the commands. We'll see the commands later. Are you clear with this PPP microcode?
Yes, sir.
Okay. So how has iOS XE evolved over the years? So initially we had 15.x releases of the iOS, which was named as BinOS, and it was only for ASR, ISR, and CSR devices. Then simultaneously we had Nova release for Catalyst switches, but with Polaris BinOS releases like 16.x releases, we merged both of them into one, and Polaris can run on all Catalyst switches, routers, and some of the other like wireless and IoT platforms as well. So it's platform agnostic. It is only the bottom layers that will be adapted to new hardware. So the software as such will be the same for all the platforms. The release strategy, these are like Denali releases. They were earlier named on mountains, and now it is being named on cities. So 16.1, 16.2, 16.3 are Denali, 16.4, 5, and 6 are Everest, 16.7, 16.8, 16.9 are Fuji, and Gibraltar is 16.10, 16.11, and 16.12. There are later releases like 17, 17.1. Those are named after cities like Amsterdam and Bengaluru. So those are the latest iOS. So one thing to note is earlier we had different operating system for routers and switching platforms, but now both the flavors are merged and we have Polaris releases. So this is what I was talking about. So this was traditional iOS, the BinOS, what we call. So it had iOS running as a daemon and feature component, a common infrastructure management interface. This is similar for Nova was for switch platforms, but with Polaris we have merged both of them into one. And there are certain database option added as well that helps in storing the data of the state of the FP and RP in a consistent format. So we have something like AOMDB, Crimson DB for that support. We can also host the applications now on the devices with the help of the LXC and KVM functionalities. So this is again the BinOS. It was Linux-based platform. So it had multiple processes, but it had a monolithic IOSD process. The main thing here is we have two different things. One is PI and PD. PI is platform independent, and PD non-IOSD code is referred to as platform dependent. So the code that is running runs as IOSD, the daemon process, that is PI, platform independent. So that will be the same across all the platforms. But any other code that is running on non-IOSD, like we have FMAN, CMAN, those processes, those are referred to as platform dependent processes. So we have something like for inter-process communication, we have within IOSD, we have watch queues, booleans, linked lists. That will be internal to the IOSD, and within BinOS, like the communication between iOS processes and the other processes, IOSD and other processes will have MQ, IPC queues and TDL queues. So for data plane, we call it CPP, also known as CPP, Cisco Packet Processor. Routing platforms only, but Doppler ASIC is for switching platforms. It's a hardware only ASIC. This is what I was telling. So the whatever processor are running within IOSD, we call it PI, platform independent. The other processes apart from IOSD running within the Linux kernel itself, they can be called as process dependent, and CPP function, the processes that are running within the data plane, they can also be termed as platform dependent. So since they depend on what platforms we are using. So again, this continuation of this. So PI is generic code within IOSD. It can be shared between multiple platforms as it is, but PD handles how these. So PI, we have generic code which can be shared, but PD, what it does is it is a difference where the same code, same upstream code, that is the PI code, can be translated and used with different hardware. So that will be dependent on what hardware we are using. That's why that becomes the platform dependent. So this is what a forwarding manager does. So it helps in it provides the platform as abstraction in IOSD process. It talks to IOSD and other BinOS processes. So FMAN for forward FMAN it will be there on both control plane and data plane. FMAN RP talks to IOSD and other BinOS processes. So FMAN RP is basically this one on the control plane, and on the data plane we have FMAN FP, so which will be communicating with our RP, and also it will be communicating with the QFP or the CPP client and CPP driver to make sure that all there is communication, inter-process communication between all the processes involved. Apart from that, FMAN also maintains a hierarchy of objects and dependencies. As I was telling, they'll be stored in AOM DB, and it will be programmed into DP once all dependencies are solved. So whenever you configure something on the control plane, they'll be pushed to the platform, the data plane as object, and they'll be programmed once the dependencies are solved. And finally, an acknowledgement will be sent back to RP. We'll see how that works in the end of this session. So going further, we have IOSD and BinOS logging. So the difference is the look and feel, the architecture, everything is different between IOSD and BinOS logging. So if you have seen earlier, IOSD logging is nothing but the show logging output that we see on the devices. So, but the BinOS logging is different compared to this one. So BinOS logging is per process logging. There will be multiple processes that will be running, like CMAN, FMAN, FMAN RP, FMAN FP. So each of those processes will be logging their own logs, and that will be in the RAM. And once the file reaches certain size, it will be returned to the hard disk. And this process is called as rotating the logs. So rotate is basically transferring the logs that are being written by processes in RAM and into the hard disk for persistent storage. Got this right? The difference between IOSD and BinOS logging. So IOSD will have only one IOS logger. All the tasks will be logging the logs to that logger, and you have a log file which you can view by show logging output. But here in BinOS, you will be having the process, each of the process logging into their own file in the RAM. Once the RAM is full, it will be returned to a disk or flash for the persistent storage. Are we clear about this?
Yes, sir.
Okay. So there is a need for inter-process communication to reliably communicate and make sure things are working fine. So we have multiple sockets here. First is the local IPC, which is for the communication between the different processes in the same complex. Like all the process within the RP or the process within the FP can communicate with local inter-process communication. Remote IPC or the remote inter-process communication, it uses TCP to communicate with the same processes of different stack members, like Fman RP communicating with Fman FP, sorry. And MQIPC uses shared memory. So it is used between control plane processes and Fman RP. So there will be a RP process running on the there will be a Fman RP process, and the communication between Fman RP and the control plane process like IOSD, SMD, they'll be using this message queue IPC for persistent communication, and it also provides a log storage, and it is also it can be restarted. Okay, so as I was telling earlier, punt is a packet that are processed by the data plane and are to be sent to the control plane. So those packets are called punt. Inject are the packets that are generated from the control plane and are being sent to the data plane. So those are injected packets. LSMPI is the transport between data plane and control plane. It is the full form is Linux Shared Memory Punt Interface. And LFTS is again within the control plane. It is used for communication with the applications hosted on the control plane. That is the LFTS. So these are the four main things. Punt are the packets that are being sent from data plane to control plane. Inject are the packets that are being sent from control plane to data plane. And the medium that facilitates this transfer is LSMPI, Linux Shared Memory Punt Interface. And LFTS enables communication with the application containers that are hosted on these control planes. Are we clear about these terminologies?
Yes, sir.
Yes, sir.
So the IOSXE is an as we know, it supports the application to be hosted as containers. So as I was telling, LXC, it provides the operating system level virtualization through environment that has its own process and network space. So the underlying hardware will be the same. The Linux kernel will be virtualized, and we can host multiple different containers with its own process and network space, so that we can add multiple capabilities to the routers. For example, we saw ISR was on ISR 4K devices. We can also host REST API for netconf can be configured on these using these application containers that will help in better management of the devices. Let's see the B trace. B trace is basically the binary tracing, basically the logging that we saw earlier by the BinOS processes. So classical logging, as we saw, it will be logged as a simple string. It will be with a particular path and the log message. It will be with a particular pattern and the log message. But with binary tracing, what happens is each process will be running its own log file, and it will be adding the logs to that file, which will be present in the RAM. And once the file is up to the limit, it will be returned to the hard disk and started from the beginning. So that will enable us the persistent logging. So these btrace files, they'll have to be decoded separately. So once the file is being generated, they'll be in a zip format, gzip format. So they'll have to be decoded separately, and then only we can see the contents that are being written by the processors. So there'll be one active trace log per process. So IOST will be adding its logs to a file named iosrp, and this will be a timestamp .bin extension. fman-rp similarly will be adding its it will be adding its logs to this file fman-rp. fman-rp, and the process is present on R0 with the timestamp. FRU is field replaceable unit, so it will also add the module that it is working on. So this file path that we see, it is on the RAM. Once it is the file is being the limit of the number of logs is being reached, they'll be written into the hard disk and can be stored for the persistent storage. And similarly, CPP client, CPP driver, they'll be writing their own logs, and these are the process instances, the process IDs. So basically, if you see this one, it's the CPP CP process, CPP client process that is running on F0 with the process instance of this one, and this is the timestamp. So this is how we read this particular file path, and eventually these logs will be written to the hard disk. So as I was telling, once the trace log is full, it is gzipped and moved from the RAM file system to boot flash or hard disk. There will be a maximum size defined, and after that, the older files will be deleted. Trace logs, they'll have a sequence number per PID and increments when rotated. So these are the trace logs, and retention is basically done by storing it in the hard disk for persistent storage. If the number of trace log file is deleted, the oldest trace log files will be deleted. So btrace logging levels, same as the classic iOS logging level, we have different levels: fatal, emergency, alert, critical, error, warning. By default, it will be in notice. If we by default it will be in notice. If we can also increase it to information, debug, or verbose level. So debug, verbose, and noise, it will generate more and more logs, and we can enable this per process using this command: set platform software trace, the process name, chassis, active R0 on R0. For this process, we are setting the log level to debug. So that we can have the logs collected during the issue state or when required. So decoding the trace logs, we have multiple internal tools where we can decode the trace logs. These are not human readable. They'll be decoded in the while being rotated into the hard disk. So we'll have to decode these and read the logs from the decoded file. So to check the logging, the process logging, process logs before they are being written into the trace log directory, we'll have to use this command: show logging process and the process name. to check the logs that are after the rotation is done, we'll have to get the file from the device, decode it internally, and check the logs. So this is about decoding the trace log. So as I was telling, we have an underlying Linux kernel that hosts the iOS as a daemon process. So we can access that Linux shell as well, but it needs an extra access permission. So we'll have to enable the shell access from the config terminal. These are the commands: the service internal, and platform shell. After that, if we execute this command, it will throw a challenge for which we'll have to generate a response and enter it. This will be valid only for 10 minutes. So once the challenge is, once the response is accepted, we'll be into the Linux shell, and it will be similar to other Linux platforms that we use, and all the commands will be executed. But in the production devices, entering the Linux shell is not advised because it can cause unexpected behavior. But as for your knowledge, this is how we enter the Linux shell. There are certain situations where we have to enter Linux shell and collect a few outputs for further troubleshooting. So this is how we can enter the Linux shell.
Sir, can you give any kind of example for like when we have to do these things? Like what are the tickets when
Sure.
we get?
So say we have the router prompt that we get, right? It's the iOS process, iOSD, that is running as a daemon. But there are other processes like chassis manager, forwarding manager. Those processes, if there is a memory leak, for example, those processes are obtaining the memory, but they are not releasing them. Or there are some caches, the cache memories that are being used, but they are never being freed. In those scenarios, we'll have to log into this Linux kernel. We'll have to check the memory that is being used, and there are options to free the memory as well. That is one thing. And sometimes, for example, management interface, right? So the management interface, it won't come through the forwarding plane. So in that case, the normal packet captures or the packet trace, it won't work. So in that case, we'll have to take a packet dump on the control plane itself. That is when we would need the access to the Linux shell. So these are some of the scenarios. And in some of the bugs, we'll have to like verify a few register values to confirm if we are hitting a particular software bug. So in such scenarios as well, we would need the system, the shell access.
Okay.
So let's check how the packet flow works in detail on the ASR1K platform. So we have ESI links between all the modules from ESP to all the modules. So that will basically help in forwarding the packets from SIP to the ESP and back to either SIP or RP. RP from interconnect to the CPU, we have 10 Gbps Ethernet link. Now this is a packet life. So it is received on this SPA. The SPA aggregator classifies it either as a high or low, and then over the interconnect it will be sent to the QFP or the ESP, where on the ESP connect it will be sent to the PPE for further processing, and once the PPE processes it, it will be sent to the BQS for queuing and scheduling. Once it is done, if it is destined to other device, it will be sent to the corresponding exit ports. In this case, it is a different SIP module. It will be sent to this SIP module where it will be put on the wire. If it is destined to the same device from the interconnect, it will be sent to the RP, which we call as punt. So this is the basic packet flow in the ASR device. So when the packet is received on the SPA, it will be classified with the ingress classifier and it will be put in a buffer. And if the interconnect is free, it will be sent across towards the ESP. So this is how a packet traverses in the SIP. So we have PLIM statistics that we can find to check different kind of parameters like good frames received, bad frames received, broadcast frames. Those kind of values we can check here. And as we were discussing earlier, SIP maintains the drop statistics as well, so we can get to know if any packet is being dropped at the SIP level. So we can check how many packets were received in the ingress direction, how many packets were received in egress, and how many of them were IPC packets. So these are different PLIM statistics that we can. PLIM is physical layer interface module. So this is a driver that exists on the SIP. So we can check the PLIM helps us to get the statistics of all the packets that traverse through a SIP module. We have per port PLIM counters. So if you see here, it's for port 007, and we have per port PLIM buffer as well, platform QoS. So we have different outputs. Like in this per port, we can check how many low priority RX packets were there, how many low priority TX, how many high priority RX, high priority TX. And among RX packets, if you see here, these many packets were received and these many were dropped. So based on this, we can confirm that the packets are being received, are being dropped on the SIP itself, and they are not reaching the QFP. So this is how we check if there are any drops on the SIP modules. Are you clear with this?
Sir, once we identify that the packets are dropped there,
okay,
then what are the steps?
Yeah. So basically, when the packets are dropped, it usually means that the SIP is being overwhelmed with traffic. So basically, the ingress buffers are getting oversubscribed. I mean, it's already full, and the packets that are coming next will be dropped till the buffer is free. So we'll have to check at the back pressure, like whether the ESI link is also oversubscribed. Because of that, the packets are being overbuffered here, or whether it is some issue on the SIP itself. There can be internal link issues as well. So once we get to know that the packets are being dropped on that, we can further focus on isolating what is the exact issue.
Okay.
So there are a bit of changes on ASR1001X device. So when we are checking for the PLIM status, so this one gig 000 will be actually PLIM interface 003. So 10 gig 001 will be PLIM 000. This will be 001. Crypto engine internal will be 002, and 003 to 008 onwards we'll have 6 gig interfaces. So if we if we want to check the PLIM outputs for 000, we'll actually have to check the interface for 003. The physical interface is 000, but the PLIM interface is 003. Got this mapping, right?
Yes.
Okay. So on the newer platforms, like for example, ASR HX devices or MIP100 SPA modules, we don't have PLIM. PLIM is replaced by a process known as EasyMan. So it's the same statistics, but instead of PLIM, we'll have to check the EasyMan. The outputs will be the same. So this command will show us the packets that are received by that are received and sent by Scooby ASIC towards Marmot. Marmot is the ASIC on the FP. So Scooby is the ASIC that connects the FP towards these SIP modules. So the ASIC, we can, with this command, we can confirm the number of packets that are being sent from SIP towards the ESP. And this is for slot 0. Slot 0 will be one of the SIP, so we can check for that. If there are any, like what are the number of packets that are being received and sent by the Scooby ASIC. So we have SerDes output as well. SerDes is basically the ESI link. It stands for Enhanced SerDes Interconnect. So with this SerDes output, we can check what are the number of packets that are being sent over ESI link from this particular module. towards the F0 module. What is the number of packets? So you can get packets high, packets low, bad, dropped. Those statistics you will get. Based on that, you can check if it is being dropped somewhere at the hardware level. So for a classic QFP oversubscription case, so you see that you have packets being dropped. This is how we can check. So earlier you were asking, right, if we see the drop on this particular the PLIM or the EasyMan statistics, we see the drop packets here. So it is on the RX side of the port. So RX side of the port, in the sense we are buffering it, but buffer is getting full and we are dropping the packets after that. So the next step is to check the ESI link between the SIP and the FP modules. So when you check the slot 2 SERDES statistics, for that is the Scooby link between the slot 2 and the SIP, so slot 2 and the FP, you see that the flow control count is increasing. So basically, flow control is that the packets that are being dropped because FP is not able to handle those. So in this case, the packets will be dropped, and FP, since the buffer is not available on the FP, the SIP buffer is being used, and whatever packets that are arriving late will be dropped because buffer is already utilized. So this is how you check the drops from one level to another. You got the scenario now, right?
Yes, sir.
Okay. So this is the ESP10 diagram. We have mid-plane interconnect to FP, RP, and other SIP modules. So once a packet traverses, this is the ESP. So the packet usually is received from the SIP. It will be put into packet buffer, into the packet processor engine. Once it is processed, it will be put into packet buffer DRAM. From there, BQS will schedule that packet and send it out of the respective SPIs, SIP, sorry. So let's see the packet flow. So global packet memory is a memory where it is per interface memory, and if it is full, then we see these overrun errors because the buffer is already full, but we still keep receiving the packets, so those packets will be dropped. So that we see as overruns. And now once the packet is in this buffer, the PPEs will process those packets, and after processing, there will be the global packet memory is the on-chip location where we can buffer the packets before the PPEs can process them. Once the PPE has completed its processing on the packet, it is sent to larger chip, that is the buffer DRAM. And once from the buffer DRAM, the BQS will take over the packet and it will schedule the queue and schedule the packet accordingly. So once the packet is handled by the packet processor engine, so it will each packet processor engine will have multiple threads. So the one of the threads will handle that packet, and after that packet is handled. So I was telling about the field invocation, feature invocation array, right? So once that thread gets that packet, it will match with all these layers. So first XConnect and then L2's header. Now we found that it's a IPv4 packet. So we check the input feature invocation array for that interface. We get all these features. We apply these features, and if ACL is is configured to block that packet will be dropped here. But if it is permitted, then we further proceed. So similar to that, all the other features are applied. And once those features are applied, we check if it is, there are three scenarios. If it is IP unicast, it will be checked for the direct forwarding lookup. If it is IP multicast, it has to be replicated and then forwarded. If it is packet for us, it has to be sent to RP, which is punted. So again, once this is confirmed, it checks the output feature invocation array and again applies the output features that have to be applied. And once it is done, it will send out the packet out of the. It will store the packet in the resource DRAM. So this one, this is the command to check the feature invocation array for each interface. So this command will give the FIA for gig 000. You got this particular flow, right? This is very important.
Sir, if you can go once again.
Sure, okay. So we get the packet from the SIPs, right? From the ports. Through the interconnect, it will be put into this packet buffer. And once it is put into packet buffer, there will be multiple thread. One of the PPE will handle that packet now. Now say the PPE2 will handle. So PPE2 in turn will have 4 threads. Among that, one of the threads will handle this packet. Now we got the thread 3 to handle this packet. Within what that thread 3 does is, it will check for the corresponding headers. For example, here we have XConnect L2 header, IPv4, IPv6, which is layer 3, then MPLS. Corresponding header is checked, and for that particular feature, for that particular thing, we'll have a input feature invocation array. So basically, on the interface, you will configure different things like ACL, QoS, or you will have something like for QoS, you will have markings, you will have NAT. So those are the features you can have in either input or output direction. So the features that have to be applied on input direction are found in input feature invocation array in this order, and the features that have to be applied on the output direction are output feature invocation array, which has to be applied in output direction. So once the packet is in the thread, it will match all these features and check if it has to be applied on that particular packet or not. If it is applicable, it will apply the feature. And once the feature is applied, we'll see how to further process the packet, whether it is IP unicast, IP multicast, or packet for us. Packet for us is the situation where the destination IP belongs to us. Like I was giving the example earlier, right? If the 10.0.0.1 IP is on the device itself and we ping from any other device, the ping packet that we receive, it will be packet for us packet. So this packet will be sent to RP and not out of the SIP to any other device. So that is packet for us. IP unicast will be directly, the forwarding table will be looked directly, but the IP multicast, first replication takes place and then the forwarding lookup happens.
Okay.
And similar to the input FIA, we have output FIA as well. And each of these features, if applicable, will be applied to the packet. And once everything is done, the PPE will be ready for to store the packet in the buffer. So I was telling the feature invocation array, right? We'll have these kind of things. So for example, we have IPv4 ACL, and we have style legacy is for NetFlow, QoS is applied, NAT is applied. So we apply all these features on that packet if applicable, and then once it is done, we'll send it towards. We'll check whether it is for us or input data or multicast. Based on that, once the output interface is determined, these IPv4 output features are applied. NAT output, output style legacy, output IPv4 output QoS. So these features are applied on the output packets before the packet is actually sent out. Got it, right? How feature invocation array works.
Sir, are there any commands that we have to learn for all these processes?
Yeah, this is the command. This command will give you the output that I showed in the next slide. This one. This command, show confirm hardware QFP active interface. For that interface, if you see this one, it will give you the feature invocation array.
Sure.
So once we are sure about this thing, the thread will put the packet into, and if we drop anything within that thread, right, because of any ACL or anything, that drop counter will be incremented, and we can see those drops in this output. Show platform hardware QFP active statistics drop. So here we'll see multiple reasons. So based on what reason we see, we'll have to check why the packet is getting dropped. So we can check the statistics as well, what kind of packets are being handled. IPv4, MPLS, XConnect, those will be different types of packets. Now, once the packet is being processed, it will be stored in the buffer DRAM if BQS is busy. And once the BQS is available, it will queue that particular packet. If QoS is applicable, it will apply that QoS. And once that is applied, it will schedule and send the packet out of the out towards the interface and towards the exit interface, where SIP takes the packet and sends it out. So QoS processing, we have different options: classification, marking, policing, WRED. Classification will just classify the packets. Marking will add the bit on the packet, which will mark the packet. Based on that, we can police later, and we have random detection option as well. All these tasks are performed by the traffic manager of the QFP, and we have 3 parameters possible, which is minimum bandwidth, excess, and maximum. So minimum bandwidth we can apply. If it is excess, we can apply bandwidth remaining, and maximum will be shaping it. This is QoS processing on ASR1K. Now, how a IPsec packet is handled. So once we receive the packet, it will be sent to PPE. The PPE will apply the feature invocation arrays, and it will buffer the packet. It will look up in the TCAM for the corresponding group ID for the IPsec, and it also checks the resource DRAM for the class group ID and obtains the crypto SA values and all those things. Once it is done, it will be sent to the queuing and scheduling, and back to the interconnect. From interconnect, instead of SIP, it will be sent to the crypto chip, where that particular context ID is obtained, and the packet is encrypted or decrypted based on the requirement. And once it is done, it sends it back to the PPE. It will be handled with different capabilities, like the IP, source and destination IP might be changed, or there will be some other changes in the packet. So based on that, it processes, and the packet will be further processed and sent out to the SIPs. So this is how a IPsec packet is handled. So once the packet is received from the ESP on the SIP module, it will be buffered in the egress buffer if the SPAs are overwhelmed, and if the SPAs are available, that will just send the packet out of the SIP module. There is no egress classifier like we have ingress classifier. So in short, if we look at the high-level packet flow, so we receive a packet and classify it either as high or low by either SPA or SIP. Once the packet is classified, it will be sent over to the QFP, where it will be stored in global packet memory. From the global packet memory, a free PPE thread is assigned to process the packet. It will apply all the FIA features, feature invocation array features on that particular packet, and processes the packet. Once the packet is processed, it will be released. The packet is released to traffic manager, and it will have its own packet buffer for placement of the packet into a required output queue for scheduling. From there, BQS will handle the scheduling functionality, and the packet is either transmitted out a physical interface or transmitted back to a PPP for further processing. For example, in case of IPsec packets. This is a high-level packet flow. So punt path, when we punt is basically the packets that are destined to the device. So we receive a packet from the SIP, we send it to ESP. After processing, we know that the device, it's a local device that we have to send it to. So punt to RP again have multiple reasons. For us, control is control packets that are destined to us. For us, data is data packets, and cause X are different causes. There can be multiple causes for that. So once it is punted, it will be sent to RP for further processing. And punt to recycle, in the sense it will be punted back, it will be sent back to PPE for further processing. So as we were discussing earlier, LSMPI or Linux shared memory punt interface is a interconnect that helps in traffic forwarding between ESP and RP. So that will give the counters of whether the packets are being dropped within the control plane itself. Inject path, inject is when the packets are being originated from the RP itself. So RP will directly send it to the QFP for processing. It will be processed by PPE and sent out of SIP. So this is the inject path. So if you see this one, we receive a ICMP echo request that is destined to the router. The packet is consumed because the packet is destined to the router, and then it will be recycled to be processed again. Then it will be forwarded out of the device. So this is how the ICMP echo request reply works. So when there is a when any packet is being punted, it will be from data plane to control plane. But in certain scenarios, if the traffic that is being punted from the data plane to control plane is very high, then there are chances of CPU on the control plane being spiking to very high numbers, which can cause issues to other functionalities. So to avoid that, we have something known as control plane policing, where we have where we can police the traffic that is being sent from ESP to RP. Per cause policer will be there by default. So for example, if there are too many R packets being received, then there are certain policing features that are enabled by default, which will take care of that, so that the RP will be safeguarded against the burst of the packets from the data plane. So that is where we have punt path policing. Global policer fixed rate, it will be fixed to 150 kilo PPS. So if there are more packets than that, then the global policer will start to drop the packets. So these are different types of punt policer. Punt per cause. Per cause, it will be like ARP request or response is a cause. Apart from that, we have L2 control packets, L2 data packets, something like that. So each of those causes, per cause, will have these many numbers. If it moves over that, then those packets will be dropped. So this is per interface. If the number of packets per interface is more, then that will be dropped. Respective drop counters can be seen again in the under the QFP active statistics drop output. So we have different mechanisms to debugging punt and inject paths, which we'll take a look later with under the PR trace, or what we call as platform packet trace. So with these debugs, we can see what kind of where packet is getting punted or injected. This is the LSMPI level debugs. So any queries about the punt and inject?
Sir, no query, but it is a bit overwhelming.
Okay. Fine. It's fine. I mean, you will gradually get used to it. You
Yes.
can go through this again. I mean, with the packet trace and a few labs, it will be easier for you.
So, like when we get cases, we need to check all these things in the troubleshooting part.
Yeah. So basically, if there are any packet drops, right? So you first check this one, the show platform hardware QFP active statistics drop. So based here, you'll get the drop codes. So if it is something like a tail drop, you will say that there is some oversubscription happening. You'll have to check why it is happening. If it is per cause, you will say per cause per polyser is dropping. If it is per interface. So this is the first stop for to check the QFP drop. If you find any drops here, based on that, you can check for the further drops.
Okay, sir.
We'll just take a look of different processes that are running on the FP and RP. So FMAN RP, it runs on the control plane, and it maintains a persistent copy of the forwarding information base. And FMAN FP, it's the same forwarding manager process running on the FMAN on the FP module. It has a software copy of FIB and the configuration data, and also it helps in programming of these into the hardware. We have CPP client and CPP hardware. CPP client is basically responsible for allocating resources. CPP is basically the QFP or the forwarding plane. So CPP client is responsible for allocating and managing resources in the control in the data plane. The CPP driver, it provides the low-level access and control for the CPP. So if you it provides different functionalities like detecting failures, recovering as needed. So that those are handled by CPP driver. This is just for information. Just go through this so that you'll better understand other topics. I mean, there are a few cases where these some of these processes will be crashing, and so at that point of time, you need to understand what exactly crashed and what it does to understand what to do next. So IP forwarding verification, what you can do is, this is the iOS view. You would have seen the show IP route and particular IP. You will get a next hop, how it is learned, what is the prefix that you are looking at what is the exit interface route metric. This is the RIB, the routing information base. This is the FIB on the RP, the self output. So we'll get what is the exit interface, what is the output chain, how it is being sent out, what is the next hop, all those things in the FIB. Adjacency information also you will get it from the RP itself. This is the these are all our RP views. On the FP, it will be a bit different. So it will tell what kind of hardware handle is being created, what is the AOM ID, is the AOM DB, where the features will be stored. So these are just for the introduction. You can check this later. We'll just see how programming can be done, how programming is transferred from RP to FP. So for example, let's say we configure IPNet inside on gig 002 and IPNet outside on gig 003. So this we do on the iOS process of the RP. Now the forwarding manager takes this configuration, it converts into objects, and these are the objects. So domain name and domain inside and domain outside. So domain inside is for 002 and domain outside is for 003. These are the objects created by forwarding manager of RP, and these objects are sent over to the forwarding manager of FP. So here these two objects are added into the feature invocation array of those two particular interfaces. So for 002 we added the feature invocation array NAT, and for the 003 also we'll add those. Now, if we add IPNAT source list, similar, we'll have domain inside the source IP address, something like that. So that mapping will be added. So basically, whatever you configure on RP, that will be sent to FP as the objects, and those objects will be programmed into the hardware. So when we configure these objects, the RP sends to FP and it will be waiting for certain acknowledgements. But if it didn't get any acknowledgement, or if there are any errors, we can check the statistics here, Object Manager F0 statistics. So if there are any pending issues, we can see here, and further we can check what kind of issue is there. So basically, to give you an example, I had a customer issue where they had configured NAT, but the packets were not getting NATed. So when we checked that, when we checked these object statistics, we found that the NAT is being configured on the control plane, but at the data plane, it is not being programmed. So whatever the packets that are being handled by QFP are being handled without NAT. So that is when we got that particular scenario. And in such scenarios, the only option to recover is to reload the device. We reloaded a device, and the NAT was being applied at the hardware level as well. So that is when you say that configurations are configured on the device, but that particular feature is not being applied on the packet, that is when you have to check if there are any errors at the object manager level. So that is it for today.